In this video, we want to consider the evidence for the wave-particle duality. I'm going to look at electrons, and I'm going to look at light. First of all, the electrons. What is the particle evidence for electrons, or electrons behaving as particles? If we think of a GM tube collecting in beta particles, those beta particles will come in and be collected by the GM tube. When you're doing radioactivity experiments, for example, the beta particles there are electrons, and the GM tube will detect this beta radiation, and you will see that random clicks are recorded, and that indicates the arrival of individual beta particles, in other words, electrons. And so that shows that electrons have a particle nature because they arrive as individual particles. If we think about electrons then as a wave, what is the evidence that electrons has a wave? If we have electrons being diffracted by a crystal, what we find is that we have what we observe is we have a regular pattern of circles. And that's what we actually observe, this regular pattern of circles. And why that is because the atomic and nuclear spacings in the crystal through which the electrons have been passed, the spacings in the atomic spacings in the crystal has a similar size and is approximately equal to the de Broglie wavelength of the electrons. So there we have the particle nature of electrons in the Geiger-Müller tube, and we have the wave nature of electrons with electrons passing through a crystal, and we have this diffraction pattern, regular pattern of circles. Let's now turn our attention to light. Light is observed as a particle in the photoelectric effect, where we have particles of light, photons of light coming in. It hits the metal surface, and we have a photoelectron being released. One photon coming in will release one photoelectron. However, this light coming in, this particle, the photon, needs to be of a certain frequency, and there is instantaneous emission of electrons. This is because the photon energy is proportional to the frequency, and we can work it out by multiplying the frequency by Planck's constant h. And so we find that the electron is then released with that energy. If this energy is greater than that releasing energy, then that will be released with a particular kinetic energy as well. Light as a wave we can observe when we pass light through the double slits in the double slit experiment. And what we see occurring on the screen on this side, if this is the screen, you will see an arrangement of light and dark bands. Remember, these bands have equal spacing, where we have the central maxima and we have the minima going out from there. And we see this pattern of light and dark bands of maxima and minima, maxima and minima. And this is because the waves can reinforce and superpose to produce these fringes. And so the diffraction grating, or the diffraction at the slits, causes the wave to overlap. And so this shows the wave nature of light. Photoelectric effect shows the particle nature of light. So in summary, what we have is that electrons have both a wave nature and a particle nature. Particle nature of electrons is shown when the Geiger-Müller tube collects the individual electrons. The wave nature of electrons is shown when we have a circular, regular pattern when passing electrons through a crystal. The light has both particle and wave nature. The photoelectric effect is evidence for the particle nature of light, and the diffraction pattern when light is shown through diffraction slits shows the wave nature of light.